Hi everyone, thank you all for coming. I will present myself just in a minute. What I want to do in this talk is talk about reactive. And reactive is a word that has been used in many contexts, and it's not always clear what that means. And so I'd like to give you at least my version of what a reactive web application is in practice. So not only the theory, but also the how it looks like in code. So I will start with giving you a quick theoretical introduction into the evolution of web application architecture over roughly the 20 past years. Then we'll also talk a bit about hardware, and then we'll code and hopefully see it work as small reactive web apps as well. If there is time left, I'll also talk about deployment and load testing, but we're on a short schedule, so we'll see. And afterwards, if you could keep your questions for the end, that would be great, because then you can keep in the flow. A few words about myself. My name is Manuel Bernhardt. I've been working with web applications for a long, long time with Java, and then in the recent 6 years with Scala as well. I work as a freelance software consultant. I live in Vienna in Austria, and I'm actually done writing a book called Reactive Web Applications. It's 390 pages, and in 1 hour now or 50 minutes, I will tell you everything about the book, or I will try at least. Let's see how that goes. Oh, and Manning just informed me there is a percentage, 39% off of the book if you're interested. If after the talk you still think this all makes any sense at all. So let's start with the history of web application architecture. So in the beginning, what we had was, the good old days. It was really easy and simple. We had HTML files if you had a DOS computer, because there was no space for HTML. You only had HTML, 3 letters. And then you had, the obligatory GIF file that shows you the construction of a website, showing that it's not finished. And then there's probably also some broken links. And that was good because you only had to take these files, put them up on a server, and that's it. You had nothing else to do. So that was easy, that was fun, that was nice. So a few years later, especially in the Java world, we ended up with the 3-tier or lasagna architecture. Who has worked on exactly this stack here? With the, so that was fairly popular. You had Apache Web Server, Apache Tomcat, and some stuff, and then MySQL, and that was good. There was only 2 arrows. So the work was still okay. Sometimes one of the arrows would break, but most of the times it was okay. This was simple. And then we got a few years later. What's the next big thing? What came after that? Can anyone tell me? What's the next big architectural thing that everyone talks about? MVC? Yeah. In terms of deployment architecture.
Rich internet applications.
Yeah, in that direction. I will give it to you. It's the cloud. What I mean here. It's this, It's when you end up with many arrows that go around, and many different things that connect, and it's a bit like this. You end up wondering what you've done, and you build them. So this is an architecture that I actually did not build, but we migrated the data away from this. So you have the data spread out on many cloud services and real databases. And what you can observe is there is many more arrows, and these arrows, they represent network operations. So there is a lot of network interaction happening there. And that's something that's going to be quite interesting, because for reasons that we're going to see a bit later. Does anyone know what's a big keyword now in terms of the next architecture, in terms of deployment architecture?
Microservices.
Microservices. So let's take the idea of arrows and put them everywhere. And you have a small little service, and then you have many things around. And if you look closely and you really focus on this image, you can sort of see the emerging pattern of this flying spaghetti monster in your microservice architecture there. I think microservices is a nice thing when you have reached a certain size of development team. If you have a small development team, maybe don't go there, because you're adding a lot of complexity. Suddenly the complexity is in your arrows that are in there. So that's what we do. The trend really is in doing more network, more computers talking to each other, more network operations. And we can imagine that we're sitting there in front of the network and controlling everything, where in reality what's happening is this is your network, and if you're unlucky, this thing falls apart and then all your connections are gone. And then or maybe they're slow and then you're in trouble. So really, that's where the reactive architectural pattern, I would call it. It's not an architecture in itself, it's something that you can use on an existing system to make it better. And better means in this case that it's responsive for the end user, so it's fast and it's there. It's resilient, and in order to get that done, you need to be resilient against failure. You need a system that is able to detect that there's a failure. And maybe you don't want the whole thing to fall apart when there's just one database that went down or just one third-party service that's not available. Maybe you want to isolate this failure. Maybe you can switch to another system and then it's good again. That's one component. The other component is that you want your system to be elastic when it comes to load. When suddenly your application is featured on, I don't know, Hacker News or something like this, and then everybody comes to look at it at the same time, you want to be able to use more computers to balance out the load and then go back in again when you don't need it. When that search is over. And the underlying idea that we're going to look at a bit later is this is all message driven. In order to achieve that, you end up with a message driven system. So that was for the software. Now there is one thing that it's easy to sort of forget about this, but hardware also evolves. It's sort of if you forget that hardware never, I don't know what these people were thinking, that this thing is never obsolete. Well, it had AOL 5.0 on it and 566 megahertz, but to our eyes now this is clearly obsolete. So hardware is a thing we need to look at. CPUs have been evolving tremendously. I think there are many more phones out there in this room that have 8 cores, and that's more than my computer here. So it's not single core, it's not dual core, it's not multi-core, even it's many-core. This is a Talira CPU. I have one of these at home and it has 72 cores. 72 cores, that means that I have 72 hardware threads at my disposal. I can run 72 things in parallel. That's awesome. That's really good and it's great. And when we program applications, most of the time we have these advanced things, and what we end up doing is something like this, where, we have this one guy that does all the work and the rest is awkwardly jumping. I don't know. So, because it's hard, because it's not easy to use all of these resources, and because the tools that we have had so far, they're maybe not there yet. It maybe is not so easy to use all of this power. And then if we look a bit farther, this is fairly recent, I think, and last December just, the CPUs, the optoelectronics, which means that eventually we will also lower this I/O barrier that we have in networks. I mean, that's going to take a lot more time still, but we're slowly getting into that direction where communications are getting faster. So really, we need to learn how to make use of different cores then. At the same time, memory has been evolving quite a bit. There is a website called yourdatafitsinram.com. And what you do on this website, you enter a number and you choose what you want. So here I have 6 terabytes, and the answer of the website is yes, your data fits in RAM. So you click on the yes, you get a Dell server, or on the you get a HP server or something. You can buy these things off the shelf and you get a lot of memory. What it means is, instead of putting things on disk and doing all the computation on disk, when you can start doing a lot of operations in memory, at least saving the intermediate state. That's what Spark does versus Hadoop, for example, and that's much faster. So that's one of the trends that we're seeing now, and suddenly the problem space has completely changed because of this evolution in hardware. And then I don't know how many of you have seen this. I was in Zurich in a cafe and I read this. Intel and another company, Micron Technology, they introduced a new type of memory. It's first new type of memory since '89, after the NAND flash, which is up to 1,000 times faster, they claim, and a lot better and a lot smaller. And this will have a huge impact on CPUs, because then the cache, the caches in the CPUs will dramatically change with this. So that's quite interesting, and so these are evolutions that we're seeing. But in conclusion, what I want to say for this theoretical part is that we're moving towards a trend where we have many core systems and we have distributed systems. And so it's becoming really important for us to know how to do the asynchronous programming part on the network side of things, and also in order to do concurrent and parallel computation. And also explicit failure handling is something that we better start to worry about in order to keep people happy when we build applications on the web. And as if you remember the picture of the network that's quite unstable, building failure-resistant things on such a network is tricky, and that's where these reactive patterns come in. So, but that's enough talking, and I will let's go and do some code. So what I want to build today is show you is not you know, it's small, but it will show some concepts. So I'll have a view HTML file that will communicate with a controller over WebSocket, and then the state on the server side is represented by an actor, which is one of the concepts I want to talk about. This is where message passing is happening. So we have message passing in WebSocket and message passing around the actor. Then we have the concept of a future in a call that we're doing over the REST API to Twitter. And we have the concept of an actor. And then there's another beast I want to talk about. It's called a circuit breaker. That's happening between these two. And I could go on and on and on, but I don't have enough time, so that's what we're going to look at today. Yes, so let's start with a bit of code. So I will. This is the user interface that's already there. I hope you can see this. There's an input box up there, and there is a send button. So it's a very you know, it's two things, and that should be enough for today. And let's look a bit at the code now. This is an application built on top of the Play framework. The language here for this example is in Scala, but you could do this in Java as well. It's just that I tend to know Scala better these days than Java. I kind of forgot the rest. This is the controller. I'm just displaying a view. And then I have a view where I have my input field up here. I hope you can read all of this input field and a button here to send a message. And what I'm doing, I'm setting up a WebSocket connection down here. When I receive a message, I log it out and I append it to the DOM tree, so I display it. And then when I click on the button, I basically just send the content of my input box off to the server. That's all I do. So let's start giving this a bit of behavior, and the first thing I want to do is set up the WebSocket connection. So what I'm going to do here is, in order to hold the state of this connection, I'm going to use an actor. And an actor is a small thing that we can use to keep state around. So it's an Akka actor. So an actor is, actors are lightweight objects. You can have millions of them running on one JVM. And what they do is they send and receive messages. They have a mailbox, so all the messages arrive in the mailbox. And they have an address, so you can sort of use this address or this reference to send things to an actor. And this is something you want to use for long-lived asynchronous computation. They have state, but the state is private in the actor. Nobody else can touch it. It's just the actor that can modify their own state. They can have children. There's a principle of supervision, so you can have a hierarchy of actors. It's just that I don't have a case here for showing you this, but this is one of the important points as well for error handling in actor systems. So I'm building here a little actor, and an actor needs one thing, which is a method called receive. And in there, I just say that when I receive a message, well, the first thing I will do is I print this out. So I say receive the message. And the message, And the first thing I want to show is just a ping pong kind of thing, so an echo server. This actor is going to be managed by the Play framework. So the Play framework will give me a reference to the actor that represents the outwards channel. So I receive things through here, but there is an outwards channel through which I send things out. So this, I will just send out a pong here of the message. Then in order to set up this message, I need to create a companion object, it's called, and in there I just define as the props of the actor, which are kind of the constructor of the actor. And so I pass the actor reference in there, and then I say props, and I say which kind of actor I want, and I pass the parameter here. So, and then I need to tell the Play framework, please make my WebSocket connection using this actor. So I say, I define a socket action here, and I say WebSocket.accept with actor. And here I need to tell it what comes in and what goes out, what types. And for this demonstration, I'm going to use plain strings, but I could also use a parsed JSON representation or something else. I could be more strict about this. So what I have here, I get a request, and then I have a HTTP request. Then the Play framework gives me the reference to out, and then I tell it, well, here are your props to build this this actor that I run like this. So this is how I tell the Play framework, please make an actor for me. The last thing I need to do for this, or no, there is another thing I need to do, but I need to tell it where to find the WebSocket, okay? So that's in a routes file. If you have seen a framework such as, well, many MVC frameworks have this now. I just tell it where to find the socket. And last but not least, I also need, in my view, to tell it where to find the URL. So I go in here and I say routes, application, socket, and WebSocket URL. All of this is compiled, so it's generated for me, so I don't have the risk that I forget to update this if it ever changes. Okay, so let's see if this works. So I'm going to say hi, and I get one ho. And you can see here, I received the message hi, so this works as kind of ping pong. Okay, so that was our first part, the easy part where we set up this two-way communication. So the next thing I want to do, I want to go and connect to Twitter. So for this, I need OAuth credentials because Twitter uses the OAuth protocol for this. So what I did here, I just set up some boilerplate. So you can see it uses the configuration to read out all sorts of keys. So I get a key and a token, and I can use that in order to access Twitter then. So what I'm going to do, I'm just going to say that I'm using the WS or Web Service API of the Play framework, and I'm going to make a call to this tweets.json API. With a query parameter Q, which is the query I'm running, and the message is the one that I receive. I also need to sign this request, so I'm using an OAuth calculator here, and then I pass in the key and the token. And all of this, in order to do it, I need to take the credentials, and I just pass them in. And then I have this here. And what I'm going to do now is I want to place a GET request. So this is sort of my, my request to the server. So this thing is what we call a future. A future of a WS response, like this. Yes. A future is a container for a value that's going to be there eventually one day, or hopefully a bit earlier than one day. So either it succeeds and we end up with a result of the type WS response, the one we wanted, or it fails and then we don't get the value, but we keep the exception, we keep the failure somewhere. But we keep it to ourselves, we don't blow up, we just keep it there. It's for short-lived asynchronous computation. You have one piece of state that's going to be there or not, but that's about it, more or less. When you have truly asynchronous code, what happens is there is no thread that's being held onto while the other party replies. So that's the interesting thing that this does. So I have my future here, and what I'm going to do in my first implementation here is I'm just gonna send it out to the client, okay? So let's see if that works. And it doesn't work because I need a thing which is called an execution context. You can think of this as a thread pool. It's the thing against which the future will run, which will take care of the future to run. Now here we are in the context of an actor, and an actor itself, in order to run its stuff, it already has one of these guys. So I could pass it in here, execution context, but I'm going to work more with this future later on, so I'm going to declare it as an implicit value. So I'm saying here implicit. Implicit says, if it's there somewhere in the context, just grab it and use it. So I'm declaring this execution context, and I have an actor has a property called context, and this thing has a dispatcher, which happens to be an execution context. So when we have this, that should work. So here we go. Who knows what's best to query on well, it's already there in autocomplete. So cats on the internet, there should always be some kind of answer. And yeah, here we go. That's not very nice, so let's make this a bit nicer. Yes. So what I did here, I didn't change anything in the server side. What I did in the client side, I'm parsing the JSON and I'm appending the text of the tweet. So if I reload here, I get tweets about cats and lots of Japanese tweets about cats. It's always like this. Yeah, so this kind of works, this round trip works. Now, the next thing that's important in a reactive application is error handling. We haven't done any so far. So in order to simulate, or in order to test this, I will call Twitter and ask them to shut it down for a minute. So no, let's simulate that there is a problem with the network. So in order to do so, I will do something quite nasty. I will set a request timeout of 1 millisecond. And I don't think the network here will manage with this. So I'm reloading, and now I'm looking for cat. What do you think will happen? Does anyone have an idea what will happen when I do this?
Nothing's going to be displayed.
You said nothing?
Yeah, nothing.
Nothing, exactly, yes. So I'm sending this. I can look in my logs. I received the message, but nothing happens because it's a future, and the future captures the exception. It doesn't give it away. So what do I need to do? Well, I have the future here, so I can say recover. That's one of the ways, but recover. And here, in case of a non-fatal exception, non-fatal is a keyword that can be used here, or a mechanism that can be used in order to match only exceptions that are not out-of-memory exceptions, or things that they're hopeless. So things that are not hopeless, I will try to catch. And I'm going to print out the message like this. And I also need in my view here, which expects some JSON to come in. I mean, I could give back some JSON and have a better message protocol, which you should do if you do this for real. But in this case, I will just use a stupid try-catch mechanism here. And when anything goes wrong, I say append message, and I get the event.data right out. And see if that works. Yeah, so I get my request timeout after 1 millisecond. I have recovered the failure. But I'm still not happy. And the reason why I'm not happy is because I have a future inside of an actor. And if you have a future inside of an actor, an asynchronous computation inside of a thing that's already sort of in an asynchronous context, there's a better way of doing this. It's the recommended way that the Akka team also recommends. It's using a pipe. A pipe is a bridge between a future and an actor. And under the hood, it's an anonymous actor. And the idea is that since you have an actor, and actors are all about message passing, what you do, you wait for the future to complete, which means either it succeeds or it fails, and you send the result of this computation out to another actor. So let's do that. In this actor here, I'm first going to define my protocol for handling these things. So I have either a search result, which is the result, or it's a case class, and then I have another case class, and that's a search with failure, and that's just my throwable here. And then, instead of printing out directly, what I do, I wrap this in my in the class that I want, result.body. And here I do the same, so I wrap it in a search failure. And then I'm using this pattern in order to pipe to myself, actually, in this case. So myself, because there is no one else. In a more complex system, you would delegate this to someone else to do the failure handling, depending on the case you're in. But in this case, I'm just delegating to myself, and then what I do is I match these things. So in case of a search result that I receive, I'm just sending it out. And in case of a search failure, I do the same thing as before. So again, I'm sending this out at C. So in theory, this should do exactly the same thing as before. So let's see, cat. Yeah, this fails. And if I remove my request timeout, this still, this sort of works again. Okay, so we are very good. We have used the right way of doing failure handling, in this case with my future inside of my actor. Now, the next thing I want to show is a thing called a circuit breaker. You know these things from electric circuits. When there is a power surge, you hear it clacking and all the lights go out. And but your electric appliances didn't all fry. So this is more or less the same idea here, and you use this in legacy systems or in systems that are, they cannot handle so many requests at the same time. Kevin Weber from TypeSafe, he used to work at Walmart before, and they used this a lot because they rebuilt their whole Walmart Canada website portal, very nice and so on, but they had all these legacy systems there. And in order to protect these systems against failure, they used circuit breakers, and then when the thing would break, they would use a backup system or do something else, but be nice and considerate to the end user. The idea really is to prevent cascading failures in these systems, because once it surges or is overloaded in one part, it quickly gets overloaded everywhere. So let's see what that looks like in code. I'm defining a breaker, and that's a new circuit breaker. And here I need a scheduler, which sort of ticks and gives me the evolution of time. So in this case, I'm using the scheduler of the system, context system scheduler. That's good enough for me. Then I need to tell it how many failures can I have before I trip. So I'm using 2. Then I need to tell it how long I'm wrapping a future in this, so how much patience do I have before I trip. And then finally, when the breaker will reset itself here, in this middle arrow here, how long do I wait before I say, okay, there was no failure during this instant of time, and now it's okay, I can close again. I'm confident that this will work. So the reset timeout is 2 seconds, and this, or no, let's make it 5 seconds. I also need this thing to know about seconds, so I'm gonna say, so this is a bit of a nicer way of dealing with time units here. So I have a breaker, and now I wanna use this breaker, and so I don't wanna catch exceptions anymore. I want my thing to trip, so I'm removing the recovery statement here. So I just have this mapped result in one way. That's another future. And now I'm going to use my breaker and protect my call. So call with circuit breaker, and then I have my eventually my result. No, it's not. It's wrong call. Sorry, with circuit. Yes. And then the result of this, which is still a future, I pipe to myself. So I just protected the call to Twitter because I'm going to press really, really fast, and then Twitter will be overwhelmed. No, I cannot do that, but I will again use the same trick. So I will say with request timeout 1 millisecond. So let's reload this. So now I'm gonna do 2 calls, 1, 2, and then the third one. And one thing about the Play framework is that usually it detects code changes and it reloads. In this case, that didn't happen. So you see it took a bit longer to reload and should have recompiled now, in principle. So, okay, let me just, sometimes this mechanism doesn't, okay. So about that. Oh no, I know what happened. I was expecting something to show up here, and I forgot to implement one part, which is this part. Now it's there. It's convenient. I'm just logging out, so I have callbacks on the breaker, and whenever it changes state, I'm logging out that the state has changed so that we see anything at all. Otherwise, it's not really interesting. So let's run this again. So 1 time, 2 times, and now the breaker is open. And after 5 seconds, now it's half open, it's going back. But now as I do more requests, they keep on failing, so it's open again, so I'm never closing again. So yeah, I'm kind of stuck in this loop, which is kind of not so nice. So what I'm going to do is I'm going to cheat for the sake of showing you that I'm not telling you lies and this thing really works. I'm going to define the timeout here as a variable. I start with 1 millisecond. And then when I'm half open, I'm resetting that to something that it can handle, like 1 second. And I'm using the timeout here. So it will first trip, then when it's half open, it will have the right value for the timeout, and the next request should work. So let's reload. So the breaker is open. It's half open. Now the timeout has changed again. And now you can see that the circuit breaker is closed and I get my results. So that seems to have sort of worked. And I think I'm a lot faster than when I was giving this before, so that's good. We'll have more time to talk and show you things. So I could have shown you a lot more things, I realized, but that's good because we'll be able to talk about deployment now. Is there any question for this 3-part now at the moment, or do you? Yeah.
So, did I understand this correctly? Reactive means, in principle, asynchronous callback.
Reactive means asynchronous callbacks, plus failure handling. But I would say at the level of an architecture. So it's not only at the level of the code. I just showed it to you at the level of the code. But the next thing, the deployment part, what I want to talk about now is the level of the whole deployment on operations as well. Let me talk a little bit about deployment, and let's do the questions in the end. So you can deploy this thing on one server easily, the Play framework. You can generate a Docker image, you can do a zip file, you can do whatever you want. But if you really want to have a reactive application, you want an elastic deployment that can deal with hardware failures and these kind of things. And that's not easy to do. I mean, if you have a large DevOps teams, by all means, go for it if that's the kind of business you're in. Otherwise, I would recommend to use a managed service or a solution. And I'm going to quickly talk about two here. The first one is the type-safe conductor. They're not paying me for saying this. So this is something I find quite nice. This is a thing which sort of setups and manages your whole cluster. So you can have one application and your database and what's or not, and it sort of spreads the whole thing out and manages the cluster for you. You can also throw in some Docker images, and you can have a sort of very heterogeneous landscape there. What I really like about this is they managed to fix, I mean, they can detect network partition on their own. So they use things called CRDTs, commutative replicated data types, I think, which sort of detect, if let's suppose like some of the nodes here, down there, they get cut off. These three guys, or this guy gets cut off here. It would know how to. It would know that it's cut off, and it's not the rest of the world that disappeared. And that's a really hard problem to solve because, you know, after all, the node that gets cut off could say, "Hey, I'm the one that's still there, and everyone else is gone." But if you don't solve this, at the end, when the network is up again, you end up with inconsistent state. So you want the node that goes down to shut itself off and go away. That's what you want. So that's one thing. Kind of for larger applications. For not so large applications, I'm using this thing called Clever Cloud. Again, they're not paying me for saying this. I should really ask money for that. This is something where you can just commit your code into Git, and it deploys the application, and it scales out automatically. And that's how it looks like. It's that you can select horizontal scaling, where you say, I want to go from 5 to 20 nodes. That's my parameters. And you can say vertical scaling. Each instance should go from XS to L here. L being something with, I don't know, more cores and more RAM than the smaller instances. So you have these two dimensions in which you scale. And then this algorithm is, when there is a surge in traffic, it will start deploying either more nodes or scale up the existing nodes, depending on what's cheaper. So they have made this algorithm that looks at the price as well, and they try to sort of deploy this thing so that it's cheap for you, but at the same time brings you the computational power that you need. And that works automatically, and it's very nice working with this. Since there is more time, let's talk about load testing. So the first thing I want to show you quickly, or actually not show you, but talk about is a thing called, because how do you test this? Okay, you can write unit tests and so not, but really the interesting part is what happens when there is a lot of users, when there is a lot of load. Gatling is one thing that it's an open source load testing framework, and it's built with Scala, Akka, and Nettie. And what you do with Gatling is you start this thing up, which acts as a HTTP proxy. Then you use that proxy in your browser, and you go on your application and you click around as if you were a user. And you can record several of these scenarios, and you end up with a few realistic users, let's say. And then, at the end of this scenario, which generates a source code file, you say, I'm setting this up and I'm doing nothing for 4 seconds. I ramp up to that many users over a period of 10 users, and then I send more users in, and then I go up, I have some random values here. So you describe a scenario that's a lot more realistic than just saying brute force 1,000 requests on this. And that ends up giving you a much better insight into where your bottlenecks are, where the bottlenecks in your application are. Because if you just, burst in, you will maybe see the bottleneck at the beginning, but you will not see bottlenecks that are farther down in the system. You will know how your system really responds. So this is a nice thing. The one limitation is at the moment this only runs on one computer. So you cannot, you have only one computer, so if you have a big machine, you can really fire off a lot of load from that machine, but you have only one. Oh, and that's how the sort of reports, it makes very nice reports, so you sort of see how your system then behaves and what's not working and so on. So you have a number of responses per second, and the response time distribution, you get a lot more graphs to analyze sort of how your thing behaved. And I thought I had one more slide. The next thing, another thing if you want to really put a lot of load on a system is called bees with machine guns. And that's a small script. It has a really cool name. And you do something really scary with it, which is that you give it your credentials to your Amazon AWS EC2 management console. And when it has that, you say, bees up, you start up a swarm of 400 bees. I did that once in a live session like this. And you direct that swarm and you say, bees attack that for your so in essence, and I shouldn't tell you this, but it's a system for distributed denial of service, if you like. But it's only for educational purposes. Of course, you should not use it for anything else. Yeah. And then then you can really see what happens when a lot of things. Very important, if you ever work with it. At the end, you say bees down. That's fine. But also, log in on AWS and terminate the EC2 instances. I forgot that, and then you get a bill for $150 for 1 month of running empty EC2 instances. So that's sort of the kind of tool. And there are a few more tools, but these are the two things, Gatling and bees with machine guns, which really kind of help in this regard of load testing. Okay, so yeah, I think I'm done talking more or less. Do you have any questions? No questions? Okay. Well, I mean, I'm here still until this evening. So if you have any question that pops up later on, you can come talk to me. You can also send me something on Twitter. And that's more or less what I wanted to say. Thank you so much.